Good afternoon. Welcome to the second live session interaction class for database management systems. We are at the back end of the course, and I am sure you all have been working through all the assignments and are solving the problems and getting ready for the examination. Meanwhile, we received a couple of questions, queries, and this session is actually here is a typo. This is the all of the 8 weeks of the course that we will be addressing today. So, I will get started, and as I had specified in the last live session also, we will take specific questions. There are some very general question of explain this, discuss this, which are already discussed in depth in the video. We will not be addressing those, because certainly in 1 hour we cannot do justice to such questions. So, we would specifically focus on where people have expressed doubts or have given problems that they are not being able to solve or have pointed out certain confusion. So, we will primarily focus on that. Okay. So, let us get started. The first question is from Mustaq. The question is the difference between primary key and not null. We know that while creating a table, a certain field can be specified as not null. If a field is specified as not null, then the null character cannot be, the null value cannot be put there. We will always have to specify a value. Certainly, if an attribute is a part of a primary key, then that attribute can never take a null value, but the reverse is not true. I may have some attribute which is not a part of a primary key, but still I may want the not null to be specified. So, not null would mean that I must specify the value, but when it is a primary key, then the values are expected to be unique, so that it can operate as a key, but when it is just not null, then it will need to have a value, but the values on those attributes may not be unique. Okay. The second question is, sir, can you please explain canonical cover with simple example Dhilna. You can refer to this module and slide, but since this question has been coming frequently in different forms in the forum, in the next couple of slides I will again work out examples and show how to do canonical cover and explain those. The next question again from Dhilna is how to find prime, non-prime attribute, candidate key, super key with a simple example. Again the module and slide are mentioned, but we will work out an example today. The next question is from Shomil Vacheta. The question is, what is pure query language? How is it different from other types of query languages? I mean, frankly speaking, I did not understand the question. I know pure query, I mean something called a pure query, but is not exactly a query language, but IBM's paradigm for writing Java database applications. I am not sure whether you meant that or you meant something different. So, please provide a reference or link as to what your question is, and we will get back to you on the forum. So, now let me in the next couple of slides go over the issues of canonical cover and the key, primary key, and those related issues. So, again I would remind you that an attribute of a functional dependency is defined to be extraneous, meaning not necessary, if we can remove it without changing the closure of the set of functional dependencies. So, if you are given with a set of functional dependencies, then an attribute in a particular functional dependency is extraneous if even after removing that, if we can get the same closure for the set of functional dependencies. So, to compute on that, we need to go over the canonical cover. So, if we have two functional dependencies, alpha 1 determining beta 1 and alpha 2 determining beta 2, then by the union rule we get alpha 1 determines beta 1 beta 2. whole set of attributes on the right hand side. So, we will find the functional dependency alpha determines beta with an extraneous attribute either in alpha or in beta. It could be on the left hand side or it could be on the right hand side. So, given some other functional dependency, we can identify an attribute and want to find if it is extraneous on the left hand side or if it is extraneous on the right hand side. So, if we find that, then we will delete it from this functional dependency until f does not change. So, the process iteratively could be that you take an attribute in alpha determines beta, say on the left hand side in alpha, remove that and compute the functional dependency with the remaining set of with the whole set of attributes and see whether the closure of these functional dependencies have changed or not. If it is not changed, this is extraneous, you can remove it. If it is, then you cannot remove that. So, let us look at some workout example on this. So, let us say that we have a set of functional dependencies as given here. A determines B C, B determines C, A determines B, A B determines C. So, we want to find the canonical cover, and for that we need to identify the extraneous attributes. So, we can see that for the union rule, I can see that there is one functional dependency here and another here, which has the same left hand side. So, this is alpha 1 determining beta 1 and alpha 1 determining beta 2. So, beta 1 is B C and beta 2 is B, and naturally alpha 1 is A. So, if we combine these two, then we get A determines B C, which actually already exists in the set. So, the revised set now becomes this, which means that this particular functional dependency has got removed, because it is not necessary after the application of the union rule. So, the functional dependencies have become smaller in that way. So, now we look at let us say if we consider this functional dependency A B determines C, and I want to see is A an extraneous attribute in A B determines C, that is A B determines C. So, I want to see if is A extraneous, is it unnecessary. So, what I will do? I will remove that. If I remove that, I get a functional dependency B determines C, and I see which B determines C is already there. So, we can check that if we remove this A determines if we remove A from A B determines C, then we get B determines C. So, obviously, we will have the same closure set, because if we are since we are removing from the left hand side, it means that we are weakening the precondition. So, earlier we needed both the two tuples to match both on A B for checking whether it matches on C, but now if it is by B determining C, we say if it matches on B itself, then it must match on C. So, since that exists, then A B determines C becomes redundant and it can be removed. So, we have a even smaller set. So, this has got removed as well. Now, we look at we are left with A determines B C and B determines C. Now, you can see that in this functional dependency A determines B C, we want to see whether C is an extraneous attribute. So, if C has to be an extraneous attribute, then this A determines B C will become simply A determines B. Now, we can see that B determines C is already there. So, if C is extraneous, I remove that, then I have A determines B and B determines C. So, these by transitivity, by transitive law will mean A determines C, and if A determines C and A determines B is already there, then by union I have A determines B C. So, I can see that even if I remove C from the right hand side of A determines B C, I can still in the closure I will still be able to get A determines B C. So, I can conclude that C is an extraneous attribute and it can be removed. So, my simple after removing this, my simpler set of functional dependencies become A determines B and B determines C, and after this there is no change. Of course, both these functional dependencies have only one attribute each in this case on left and right hand side. So, no extraneous attribute, nothing can be removed, nothing can change. So, the final closure is set, the minimal cover set or canonical cover set, which has the same closure as the original set, is A determines B and B determines C. So, what we have got is in doing this is it is ensured that we have ensured that your F C, the minimal cover, let me write it here because this is getting covered possibly. F C plus is same as F plus. So, they have the same cover, but certainly F C is a smaller set, that is a minimal set, where neither any attribute is extraneous nor any functional dependency can be removed. So, this is the canonical cover or the minimal cover of the set of attributes. I hope this will give you clarity in terms of what we are saying in terms of the canonical cover, and you should be able to do that. Let me address the next question, which was in terms of explaining what is candidate key and super key. Somehow repeatedly this question is coming up in the forum and in other places. Please remember that candidate key is a minimal set of attributes which can uniquely identify the tuples. So, if I identify any minimal set of attributes, so that if two tuples match on those attributes, then they must match on all the other attributes, that is the unique identification condition, then we say it is a candidate key. So, there could be multiple candidate keys in a particular relation. A super key is if I add 0 or more attributes to a candidate key, then we get a super key. So, in the super key, the condition of minimality is not there. So, a super key is a set of attributes that uniquely identify a tuple, and that will be considered a super key always. So, necessarily every candidate key is a super key, but a super key need not necessarily be a candidate key, because it may not satisfy the minimality condition. For example, one example we am showing here. So, there is a set of functional dependencies, 4 functional dependencies. Those are shown here diagrammatically. EID is determining E name, EID is determining E city, EID is determining E estate, and also E city is determining E estate. So, if we compute the set of closures for these attributes in different groups, we can find that EID, the closure of EID includes all the attributes in the set. So, EID would be a candidate key for this relation. But you can also see that say EID E name, EID E city, EID E estate or EID E city E estate, all of these have in their closure all the attributes of the relation. So, which means all of them can uniquely, any one of them can uniquely identify tuples in the relation. So, all of them will be called the super keys. So, this is a super key, 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 this is a super key. So, these all are super keys of, there could be other super keys also. For example, all 4 of them you can take together and that also is a super key. But the minimality applies only in this case. So, only EID would be the candidate key. So, that is a candidate key, which is the minimal set of attributes that can uniquely identify tuples of the relation. So, always keep this minimality condition in mind, and also note that if there are, in this case of course, there is only one candidate key. So, that will have to be the primary key. Now, if a relation has more than one candidate key, then at any specific design we will specify any one of these candidate keys to be the primary key, according to which the tuples of the relation will be organized, according to which the B plus tree indexing will be primary indexing will be done, and others will remain to be the candidate keys. They will not be used in the organization, but they will continue to have the property that if two tuples match on the candidate key, they must match on the all other attributes, and they will uniquely identify the tuples of the relation. Right. I hope this will clarify the doubts. Now, let me next talk about the related question from Dhillon in finding out prime and non-prime attributes and candidate key. If an attribute that belongs to any candidate key is called a prime attribute. Mind you, these are the two terms you will have to clearly keep in mind, that this relation may have multiple candidate keys, and if I pick an attribute and if that attribute belongs to any one of the candidate keys, then you call it a prime attribute. All other attributes are called non-prime, which means these are attributes which do not belong to any of the candidate keys. So, we are showing a relation R which has 8 attributes A to F, and it has 4 different functional dependencies. So, from this we would like to find out the primary key, the candidate keys, the prime and non-prime attributes. So, here is the diagram of the functional dependencies, and so if you just look at the diagram, I am just telling you in terms of intuitively how we can do these things. So, if you just look at the diagram, you can see that A is an attribute where there is no incoming arrow, which means that A does not depend on anything else, any other attribute. So, if A does not depend on any other attribute, then it must belong to the candidate key anyway. So, we can say that A will belong to the candidate key, and we try to compute its closure. So, my question is A itself the key? So, how do I know? I will check whether the closure of A includes all the attributes, all the 6 attributes. But if we compute the closure of A, we find that there is no functional dependency whose left hand side has only A. Therefore, the closure of A will only include A, it will not be able to include any other attribute. So, we conclude that A cannot be a candidate key. Now, so what can happen? So, it could be pair of keys pair of attributes, I am sorry, pair of attributes which will form the candidate key. Now, we know A must be there. So, I can form 5 different pairs A B, A C, A D, A E and A F. So, let me see what happens with those attributes. So, here if you look at for each one of them, for A B I have computed the closure, for A C also I have computed the closure, for A D I have computed the closure, and for A F I have computed the closure. So, just for reference, I have my functional dependencies are A B determines C, C determines D E, E determines F, and what else was there? Was there any other? Let me just check. So, A B determines C, C determines D, E determines F, and C determines B. So, I have C determines B. These are my 4 functional dependencies. So, as you can see here, if I start from A B, I will first have A B in the closure, then A B determines C. So, it becomes A B C, then C, as C has come in, this will decide A B C D E, then E determines F. So, A B C D. So, I can see that all attributes have come in. So, A B has to be a candidate key. Similarly, the closure of A C, first I have A C, then C brings in D E, then E brings in F, and C also brings in B through this particular functional dependency. So, that will also be a candidate key. But if I consider A D, then I will find that A D is it initially is A D, and then it does not add anything else, because there is no functional dependency with A or D or A D as a left hand side. So, the closure remains to be A D. So, this itself is a closure. So, A D cannot be a candidate key, it is not having all the attributes in the closure of A D. Similarly, A E, A F, as you find, you will find that these are not candidate keys. So, we have got two candidate key, and we find that these three pairs are not candidate keys. So, I will combine them to take triplets, which could be possible candidate key. So, naturally, if I form them into triplets, then I will have A D E, A D F and A E F. A D E, again I compute the closure, I find that all attributes are not included. So, I mean if we similarly do A D F and A E F, all closures I compute, I find that they are not containing all the attributes, and therefore, none of these three triplets can be candidate keys for the relation. So, now we will have to consider combining them to form a group of 4 attributes, right. So, if I combine and form a group of 4 attributes, I get A D E F, only one set that I will get. Now, if I consider A D E F, take the closure of that, you will find that it is only A D E F. So, it is also not a candidate key, because its closure does not contain all the attributes of R. So, now that process is over. Naturally, I did not consider triplets which had A B and some other attribute, or A C and some other attribute, because since A B is already a candidate key, I know adding any attribute to A B will keep it a key, it will make it a super key only, it will not remain a candidate key. Similarly, adding any attribute to A C will also make it a key, but not a candidate key. So, I can conclude after this process that the candidate keys for this relation are A B and A C. So, therefore, if I look into the set of attributes that are involved in the candidate key, I find that the attributes are A, B and C. So, I can say that the prime attributes of this relation are A, B and C. There are 6 attributes A, B, C, D, E, F. A, B, C are prime. So, the remaining set D, E, F are non-prime attributes. Now, since we have got the candidate keys, so with the candidate keys we can in a systematic manner we can add other attributes, and we will be able to generate a large number of super keys. So, if I add A, B, C, if I add C to it, then naturally it will be a candidate key which is non-minimum super key. Similarly, A B D, A B E, A B F, A C D, A C, A C F, all these will be super keys. There would be could be more super keys also, because I can add a 4th attribute to this now. I can say I have A B C, so I can add D to it. So, A B C D is also a super key and so on. So, this is how for this particular example we have been able to compute the candidate keys. We have found 2 candidate keys. We have found the prime attributes, the non-prime attributes, and a whole lot of super keys that can happen from the candidate key. And as I had mentioned little while ago, we find that this is a case where there are more than one candidate keys. So, when I actually define the table in an RDBMS system, then for creating this table we will use either A B or A C, any one of them as my primary key pair, and the other will remain to be a candidate key alone. Okay. So, I hope you have been able to understand these basic ideas right now. So, let me move on to other question. This next question is also from Dhilna as well as from Avinav Singh Parmar, where it is asked how to check for lossless decomposition if a relation has been decomposed into more than two relations. See, a decomposition into more than two relation is basically the decomposition is kind of should be looked at as a at every stage is a bifurcation process, that you take something and divide it into 2, take something and divide it into 2 and so on. So, if it has been divided into multiple, we can always look at a pair of relations and we can check whether that decomposition is lossless decomposition or not. So, for checking whether it is a lossless joint decomposition, these conditions, these are detailed in the slide. If you go back to the slide, you will see the same thing, but just to highlight the discussions here, that if R has been decomposed into R 1 and R 2, then naturally we need that the union of R 1 R 2, that is union of the attributes of R 1 and attribute of R 2 must make the whole attribute set of R, that is, otherwise it is not a decomposition. For it being lossless join, I should be able to perform a join. If I cannot perform a join, then naturally there is no question of a lossless join. So, to be able to perform a join, I need that R 1 and R 2 must share at least one attribute on which the natural join will happen. So, which means that a basic necessity of being a lossless join is that there must be some intersection between the attribute set of R 1 and that of R 2. So, R 1 intersection R 2 must be not null, there must be something, some attribute which is common to both. Finally, the third condition is that the common attribute, the attribute that belongs to this intersection set of R 1 R 2, that must be the key for one of the relations at least. So, this attribute set must functionally determine R 1, that is, the closure of the common attributes must be all the attributes in R 1, or the closure of the common attributes must be all the attributes in R 2, or both. At least one of these conditions must get satisfied. So, if these three has happened, the first one is the basic definition of decomposition, that the union set has to be equal. The second condition is the fact that a join can be defined, a natural join can be defined, common attributes are there. And the third condition simply says that common attributes must functionally determine all the attributes of one of the two relations. If that happens, then we can that is how to check that if a join is if a decomposition is a lossless join or not. And then if there are multiple decompositions, then you will have to go pairwise to do this check. So, here is an example that we have shown. R A B C D is a relation and the functional dependency set say has A determines B C, and we intend to decompose it in terms of A B C and A D, these two sets. So, naturally if I take their union, I get A B C D. So, the first condition is trivially satisfied. If I take the intersection, then I get A. So, there is a common attribute. So, now it is required that either A functionally determines A B C or A functionally determines A D or both. So, if I look at this, then I can see that so after decomposition what will happen? What is the functional dependency that holds on R 1? Is A determines B C, and what is the functional dependency that holds on R 2? On R 2 there is no functional dependency, because there is no functional dependency here which is involved with D. So, A determines B C means that A is the key, candidate key for the relation R 1, and so if A determines B C, then A determines A B C. So, that is a simple thing, because I can take A determines A A determines B C, do union, and I will get A determines A B C. So, in other words, A determines R 1. So, this condition gets satisfied, and therefore, I can say that this particular decomposition is a lossless joint decomposition, and you can repeatedly apply this in pairwise contexts to conclude whether the decomposition is lossless joint or not. Moving on, Tanpreet Singh, your question is concurrency concept. I mean, it's well discussed in the videos. You did not send your specific question. So, similarly for Molin Chakravarti transaction, I mean, certainly we cannot go over the lecture again. So, please provide your specific question. You may refer to the portal. There are sessions from the previous live sessions that were conducted in the last time the course was held, that was in March. So, you could the link is given here, the TA has given the link and specified the time. If you refer to that part of the video, you will get answers to some of the common questions that people have had asked in terms of these concepts, but since you have not given us your specific question, I am sorry, we are unable to answer anything. Okay, there is no question on ER diagram. Okay. Now, there are a lot of questions coming still in terms of the normal forms and how you go about with the normal forms, and some of you are repeatedly asking for further explanations, more examples. So, I will just walk you through a set of different relations and show how the different normal forms impose better and better structure in the whole design. So, normal forms are in a way kind of hierarchical in the way that as I go from one normal form to the other, I continue to comply with the previous form and add some more conditions. So, the data is getting more and more structured in the process of going from one normal form to 2 to 3 to 4 like that. So, I am sorry. So, this is starting with the example of I have a table which is not in one normal form. So, for one normal form, every thing must have, I mean there should not be no attribute should have more than one component. So, they have to be elementary, primitive in nature, every attribute value, and the values, every attribute must have only one value in the table. So, you can easily see that here or here that is violated. So, this table is not in the one normal form, and we can make it in the one normal form by just separating out these values, that is creating separate rows where these values are put in, copying naturally the common part of the attributes in the other tuples. So, this will clearly tell you one thing, that when we do this normalization from a not normal table to a one NF normalized table, in the not normal table my key was certainly employee ID. EMP ID uniquely identifies every row 123, 124, 125, but because I had multiple values here for this employee contact field, I had to create separate rows, and once I do that, naturally now the employee ID itself cannot uniquely identify. So, identify every row. So, the primary key has to change. We have to decide based on the real world situation as to whether it will be employee ID plus employee name, or it is employee ID plus employee contact or something else. But whenever such one NF normalization will happen, there will be impact in terms of the primary key of the relation, and we will have to take a relook on that. So, let us move on and take a look into the 2 NF form. So, when we talk about this 2 normal form, then as I said it is hierarchical. So, the first condition of being in 2 NF is it must be in 1 NF, that is a requirement. The second is, we see that all non-key attributes are fully functional and dependent on the primary key, or in other terms there is no partial dependency. So, let us just understand through this example. So, we have given a table where there are 3 attributes: customer ID, store ID and customer name. Now, we say that so what is the expectation? So, there are a company which has multiple stores for it, say McDonald, it has multiple places where it gives you burgers, or say CCD which gives you coffee at multiple places, Starbucks which gives you coffee, tea at multiple places. So, these are the company has multiple stores, and if we assume that the customer has an ID, maybe these stores are just off the shelf. So, they do not ask for ID, but if the customer uniquely, well, for example, a customer may have an ID because the customer may have a preferential card where the customer gets some special benefit. So, there could be Starbucks card or CCD card. So, the customer, now what is the relationship between the customer and the store? Naturally, a customer can go to any of the store. So, a customer to store, naturally one customer can relate to many stores. Similarly, a particular store can get various different customers. So, you can say that the customer, between the customer and store, there is a many to one relationship. If there is a many to one relationship between them, then certainly both of them will have to feature in the primary key. So, the primary key has to have both of them. Now, the third attribute, which is store name, I can expect that store ID will decide the store name. So, if I know that this is where the store is, then I will uniquely know what is the name of that store, what is that particular franchisee. So, there is a direct dependency. So, the custom store ID functionally will determine this, but between them there will have to be a many to many relation, which means that this pair of customer ID and store ID will be the key of this primary key of this relation. So, what do I get? I get customer ID, I get store ID, I get store name, and certainly I will have that one dependency would be like this, that the customer ID and store ID determines the store name, because that will have to be the key, and similarly store ID determines the store name. So, you can see that this S name, this store name attribute, which is non key attribute, because it is not forming a key, is dependent only on a part of this whole thing is the key, but store name depends only on a part of the key. So, only a part of the key can decide the S name. So, that is the reason we call this as a partial dependency. So, you do not need to know the whole key to find out what is the store name. If you just know the store ID, you will be able to find that. So, when that condition exists, we say that this relation is not in the 2NF form, 2 normal form. So, we can decompose and get a 2 normal form. What we can certainly do for decomposition is we have to decompose it in a way so that this partial dependency goes away. So, which means that SID and S name has to come together, and I have to divide things somewhere here between the customer ID and SID to separate out this partial dependency. So, we create one relation, and then the core relationship is between the customer and the store, which is the many to many relationship. So, that has to be expressed in the other table. So, now we can see that in this table I have CID and SID being the key. There is no functional dependency that hold on this. Therefore, both of these attributes together will have to form the primary key, whereas here I have SID determining S name, the store name, and store ID will be the functional dependency. So, all the information that I was keeping here are available in terms of these two tables. There is no partial dependency anymore, and whenever I want to know the store name that a particular customer visited, if I say what is the store name that the customer 12 visited, I will be able to find that, because I will know that she has visited store ID 13 and store ID 13 has the name downtown. So, this is the structuring in terms of the 2 normal form. Now, let us move further. Let us think in terms of what will happen for the 3 normal form, again hierarchical. So, any relation which is in third normal form must be in second normal form as well. So, which means that it does not have multi-part or multi-valued attributes, it does not have partial dependency. In 3NF, in addition, we define that it cannot have transitive functional dependency either. So, for looking at the transitive functional dependency, we take another example. We say there is a book ID which identifies a particular book. There is a genre ID which says what type of book it is. There is a genre name which we are calling here as book genre, and there is a price. So, naturally what will happen? The book ID, so if I just draw it, genre ID, if I say genre name and if I say price, then book ID will actually determine the genre ID, the genre name and price, everything. Because if I know the book, then obviously I know the genre in which it is there, and the given the genre, I know what is the I must know the genre name, that whether it is a fiction or a travel and so on, and obviously I would know the price. So, I can say that the primary key is just the book ID, and the non-key attributes are genre ID, price, which are dependent on this. But if we can see that I would also have a dependency here. The genre ID, if I say the genre ID is 2, I know the name of it is fiction. Obviously, I mean this for the same genre ID there cannot be 2 names, right. So, there is another dependency here. So, what I can get is that I get a transitivity in terms of book determines genre ID, genre ID determines genre name and book determines genre name. So, this is the transitivity that I am getting. A determines B, B determines C, and I already have A determines C directly here. So, I would like to get rid of such transitive dependencies, and that is where we do the decomposition in 3NF. For example, the 3NF decomposition for this will look like this. Naturally, you have this as a transitive dependency. So, you would like to put that together into one table, which is genre ID versus book genre or the genre name, and the remaining, which is book ID, genre ID and price, go into the other table. This is the basic 3NF decomposition algorithm that we have discussed. So, once you have done that, then naturally, the all these your book ID functionally determining genre ID, book ID functionally determining price, these hold on say table A, which is here, and genre ID determining genre name holds in table B. Now, this dependency book ID determining genre name is cannot be directly checked. Why it cannot be directly checked? Because the book ID and the genre name do not occur together in the same table. So, they cannot be checked, but we are still okay, because if I take this functional dependency book ID determines price, if I take book ID determines genre ID, which I can check on table A, and if I take genre ID determining genre name, which is in table B, then I can, as a closure of that, as a cover of that, I can get this particular functional dependency, that book ID determines the genre name. So, this clearly gives me the fact that this decomposition will preserve the functional dependencies, is able to preserve everything, that all dependencies which could be checked on the original table. In terms of being lossless, we can clearly see that the genre ID is a common attribute in this decomposition, and genre ID determines genre name in table B. So, in table B, this is the key. So, since the common attribute genre ID is a key in table B, genre ID, genre name, book genre, then we know that this decomposition is lossless as well, and this is how we have got a better structure. Now, we have the representation of this information in terms of two tables which are in the third normal form. They satisfy the first, second and third normal form conditions. So, this is how things go. Then I would not really work through these examples further. You can convert a third normal form into the Boyce code normal form. This example is already discussed in the module in the video. I have just put it up here to point you to the right place, where you could see that there is an example which there is an example in which there is one dependency. This is in third normal form, but there is one dependency which violates the Boyce code normal form, because its left hand side is not a super key. So, we can decompose and get that decomposition which makes it into a Boyce code normal form. But the point to be noted here, that once you do this, then you have a join which is lossless, because y determines z, and therefore, in R 1 2 y will become a super key, and therefore, this join is lossless, but the decomposition is not it is not a functional dependency preserving decomposition, because for example, W. So, this here W z determines V x y is a dependency that exists, but after you have decomposed, W is in one relation and Z is in a different relation. So, there is no way that you can take W z pairs together and decide whether they uniquely still determine V x y. So, this decomposition clearly shows you that how a BCNF decomposition could actually violate some functional dependency, while it keeps the join lossless. So, BCNF is a stricter condition, but it may not always be possible to get into BCNF, because you may not have the preservation of the functional dependencies. It may become really difficult to ensure that this particular real world condition will continue to be satisfied after you have done the decomposition. Right. So, these are matters that we had discussed in terms of our module. So, I am just highlighting that these are the things that you should study more. Now, going to the fourth normal form. Fourth normal form is particularly about multi-valued dependency. So, when you have multi-valued dependency as in here. So, we have seen earlier the issue of multi-values. So, a course and instructor, given these two pair, the textbooks could be multiple. There could be multiple textbooks that have been recommended. So, for that you specify them into separate rows. Same thing happens here as well. Now, naturally, this is where your basic information is getting fragmented. So, you could normalize this in the fourth normal form by getting rid of the multi-valued by taking care of this multi-valued dependency by putting these two together here and putting the course ID and the textbook together, and with this decomposition it will satisfy the fourth normal form. Of course, as I had mentioned during the lectures also, that it is very typical for database designers to usually go up to third normal form, because most of the real world scenarios very well satisfies up to the third normal form, and the designs are not difficult to handle. Fourth normal form is selective. Some designers will try to get into the fourth normal form, others would probably not look into that in the design. So, this was about the normal form. Moving on, there was questions on storage and indexing. What is the use of magnetic disks? Now, magnetic disks, the main use of that is secondary and tertiary storage. So, at a physical level, the data has to be stored on some device, and usually this data is very huge. So, even though some of the large semiconductor memories are coming up today, they still are quite expensive in terms of per bit cost. So, magnetic disk is one of the most widely used device in which such large volumes of data can be stored. In storage and file structure from week 5, there are some problems in assignment, but you have not given any of that sort in lecture. Please explain. So, this has we know this was not given. So, in the solution that has been released, there we have tried to provide the explanation for the same. For the rest, you can refer to the corresponding position in the textbook that we are following, the Kotzelwerser's book. B plus tree and insertion and splitting confusion. Again, you will have to, this is too generic to address certainly, but you can refer to the portal, you can refer to the live session discussions that we had last time, where we have discussed this at somewhat better length. Applications database is database administrator, user and application programmers are all the same. I think we have discussed this at multiple places during the lecture also. They are obviously not the same. The user is most removed, who is just using, you are doing a banking transaction, you are transferring money to your friend. So, you are a user of the net banking system, you have no idea of the internals, you have no idea, you do not need to know any computer science, any database systems for doing that. An application programmer is one who is writing various different applications, the screens, the queries, the transactions that will need to be done for making one account transfer, fund transfer to happen from one account to the other. Whereas, the database administrator is responsible for all aspects. The database administrator would not look at typically a specific application or how that application is coded, in what language the front end is written, what is your interface with the database protocol and so on, but the database administrator is responsible for actually planning the whole database system, installing it, maintaining it, configuring, tuning that, taking regular backups, ensuring recovery in terms of crashes, the security of the database, integrity of the database and so on. So, he has a very deep back end experience for that. So, there are several differences, Ashutosh, and I please go through the slides again. You will find that at different stages we have tried to discuss these issues. I want to know how I get internship in database, and please help me how I can become expert in database. I cannot tell you how to get internship in database, you will have to just try at different places. In terms of becoming an expert, Abhimanyu, there are some of the points we have tried to highlight. Certainly, you have to master this course, follow the video, repeated viewing might give you a better grasp. Study that Kotzelwerser's book, it is like the golden, it is like the Bible, the Gita of database systems. Attempt the exercises therein and solve the different assignments that we have provided, and go to the net. There are more and more examples and problems and solutions in SQL. The more of that you do, you will get certainly a better idea. We intend to release a tutorial early next week, where you will have some more of these, and well, practice and practice. There is nothing more than doing that in terms of gaining expertise. So, you will have to continue to do that. What is database engineering, and if we were good at database, what type of jobs you get? It depends, Divya, on what level of how good you are, at what level you are good at. the large majority of jobs that are around databases are for application programming. So, there you will, it is not enough that you understand database systems well, the SQL and the basic design, a basic idea of the transactions, but you will also have to be good in terms of programming, because the applications will typically be written into some programming language which can connect to the database, either embed that or make remote calls. So, you have to be good in C++ or Java or Python, some such front end language. So, this is what is a majority of jobs lie there. Naturally, there are specialized jobs in terms of database designer, which is more involved, and usually you do not directly get those kind of jobs unless you have worked as an application programmer for a couple of years and get experience. And then finally, to become a DBA, I would assume that you need anything like 10 years of experience of having worked with big database applications, installations under the guidance of several of your colleagues, and then you will be able to get into that. Databases is one area which which is a perpetual requirement of the industry all the time. And on top of this, if you can start getting acquiring some of the skills that relate to the newer generations of databases, like the semantic databases, like the NoSQL databases, unstructured databases, and related issues of data mining, warehousing and all that, you will have ample opportunities for good jobs. Ask 16 MCQ questions. Well, thank you, Shubhadeep. Please explain the recursion with a simple example. It is outside the scope of a database DBMS course. Look in the courses on programming, algorithms, C++, etc. In week 4, there are so many practice problems in between. How to get these solutions? Refer to the slide. You will be given to the, you will be getting the solution in the provided URL link, which is available. So, the problems were given, practice problems were given, and then the solution links are given. The solutions are not provided. In some cases they are, but usually the links are given. So, please navigate and look up those links. What is the question pattern in the final examination? It will be very similar to the assignments that you are solving. So, this for 100 marks 3 hours, and there are 40 to 50 questions. The types of the questions are multiple choice, multiple select or short answer. I think that is all that I had here. Is there anything specific that I should address? Okay. So, there was NoSQL versus SQL. So, NoSQL is not a relational database, it is a semantic database which work on the networking concept, and it is something which is good for semantic data, where there are more of relationships than just the flat type of values. It is good for unstructured data also, which you may not be able to represent in terms of very specific data types, domains, or functional dependency conditions. So, it is a very different domain. I think in the previous in the previous session, in the previous year, we did some discussions and we have provided some information. So, in the forum, Himadri will provide you those links. So, look up that, but primarily that is not in the scope of this course. Inner join, I think it has already been answered. You have given the syntax, so that is okay. That is all discussed in the video. Sir, can you provide more problems in DBMS for competitive examination? Yes, I mean, we are regularly generating problems and you are getting assignments. So, well, I think you will have to come back and do the course next year. So, you will get a new additional set of problems. But actually, if you search in the net, there is a large number of problems that are available. So, we can send you some of the links. Will your course suffice for GATE? The course does not suffice for GATE. It is your it is your preparedness with the course that will suffice for GATE. In terms of the syllabus that is prescribed for GATE, we cover more or less everything that is in the syllabus of GATE. Now, whether it will suffice for it depends on how well you have prepared, right? It should. how 2NF can be related to BCNF. It is simple, any BCNF, any relation which is in BCNF has to be in 2NF, but then additionally it has to have that every functional dependency, the left hand side has to be a super key. So, that makes it the BCNF. Yes, anything else? Okay. There is one little bit of surprise that I have from the questions, particularly for this session is I was expecting specific questions on the concurrency, transactions, concurrency and recovery side, but it seems that none of you have raised any such question. So, which could mean that you have understood everything in those, but or it could mean that you are yet to actually follow and cover those videos well. So, you have not asked, but I would like to just emphasize, tell you that these are I mean, as the query side is very important, as the design side is very important. Similarly, the transactions and related concurrency and recovery, the concepts of transactions and what is required to keep the acid properties and how to keep the transactions consistent, and when do you really need a rollback and when you really need to undo or redo transactions and so on. These are very key concepts in terms of the database system. So, before the examination I would hope that you will really go through and practice those well. So, with this this is our last interaction for this particular round of the course. So, I wish all of you all the very best for your upcoming examination, and beyond that in terms of your career, in terms of using the knowledge that you have acquired in this course. I hope that you will be able to use it in your subsequent engagements, whether you are in research or you are in industry, and would be able to take it forward in terms of learning. This was just an introductory course, just to give you the foundation, and there is a lot of further in the database systems and related to learn, and I would hope that you will continue to learn and practice on those. Thank you all very much for your time and attention. Thank you.